So good evening, everyone. Let us continue our discussion. So today we shall be, briefly revising what we learned last class, and thereafter we shall continue implementing the design concept for doubly reinforced beam, and thereafter again, uh, extend its jurisdiction and try to solve how to try find out how to solve the design criteria for the flange beams. So let us start then. So yeah, so the limit state of collapse for flexure, as we discussed last class. So basically, as you can see, this is we basically discussed for the singly reinforced section. So the others are basically an extension, okay, of this concept. Okay. So yeah, so let us briefly go through it. So as you can see here, the extreme fiber for concrete under compression, the strain is taken as 0.0035. We discussed it last class. And for finding the extreme tension fiber extreme fiber tension value, we use the formula Fy by 1.15 Es plus 0.002. Okay. So Es is 2 into 10 to the power 5 megapascal. What remains variable is Fy. Okay. So it can be 415, it can be 500, it can be 250. So based on this, the epsilon SU value will change. Okay. So this is basically the strain diagram for the singly reinforced section, and this is basically the stress diagram. Okay. So it is 0.45 FCK after a after a strain of 0.002. So after that it is constant, and below that it is a parabolic distribution. Okay. And the distance between center of tension to center of compression is the lever arm. Okay, we basically denote it by Z. Okay. So as we discussed last class, so mu is equal to 0.36 fck xb into d minus 0.42 into x, right? So dividing and multiplying by d, we basically get the equation as 0.36 x by d into 1 minus 0.42 x by d fck bd square. Okay. So taking 0.36 x by d into 1 minus 0.42 x by d, okay, as a term, we take it as a k. Okay, so we can write as mu is equal to k by mu equal to k fck bd square, where k is this, and bd square, if we take in left hand side, we find this mu, this is mu by bd square k fck. Okay, so this is the moment carrying capacity at the limiting condition. Okay. So this term is basically used, will be used later on while we will be solving designing for various structural sections. Okay. So this value will be used for finding values in various tables and codes. Okay. And this all you can find in the annexure, okay, of IS 456, right? So here basically the reason for finding the x by d, okay, reason for deriving it in the form of x by d is in order to find the this one depth of like to write the x neutral axis in terms of the effective depth. Okay. So that's why that's the concept. Okay. So that's why we try to divide and multiply by d, okay, which was the effective depth. So for Fe415 condition, the xu by d, okay, value, it comes to be 0.48. Okay, we discussed last class only. So for 415 it is 0.48, for 250 it is 0.53, and for Fe 500 it is 0.46. Okay. So taking this value in this equation, basically, so substituting the value of xu by d, we get mu equal to 0.138 fck bd square. Okay, so this is an important formula. Okay, you please keep a separate note. Okay, write it down. So mu equal to 0.138 fck bd square. So this is the moment carrying capacity at the limiting condition. Okay, so for Fe415 reinforced sections. Okay. So various various questions, okay, so various objective questions come, okay, related to this. Okay, find the moment carrying capacity at limiting condition for Fe415 reinforced beam sections. Okay, so directly you have to use this formula. Okay. So the steel area for balance singly reinforced section. Okay, so for this we just equate the forces, okay, at the tension compression side. Okay, so therefore 0.87 Fy AST equal to 0.36 FCK BXU. Okay, So again we divide and multiply by D, okay, and take B and D this side, okay. So we get AST by BD equal to 0.36 FCK by 0.87 FY into XU by D, okay. So this comes out to be how much? Yeah, so if we take this is the equation basically. So we know that PT is equal to AST by BT into 100, okay. So this is the P is the reinforcement percentage, so it is equal to AST by BD into 100. So substituting AST by BD as this value, so we get PT equal to 0.36 by 0.87 into XU by D into FCK by FY into 100, okay. So again if we take this FCK by FY and bring this side, so we get PT FY by FCK equal to 41.3 XU by D, okay. So this is one more derivation. So based on this, okay, so based on this, as I told you just now, so these are the various values of X by D and PT into Fy by FCK. I think we have discussed this all in last class, so it was just a brief revision. This will be required for understanding how to design the doubly reinforced section as well as in flange, okay, flange sections. Okay. So yeah, so this is FE 250 is 0.53, okay. FE 415 is 0.48 and FE 500 is 0.46. So this is basically found by by taking the strain diagrams, okay. So if you equate the strain diagrams using the compression value as 0.0035 and maximum strain in tension as 0.87 Fy by ES plus 0.002, so you will get these values for different steel sections, okay. And using the last equation previous, so using this we get the PT Fy by FCK value as 21.97 for Fe250, Fe 415 is 19.82 and Fe 500 is 18.87, okay. So all of these are in percentages, okay. So yeah, so in terms of x by d, mu expression is given as 0.36 x by d into 1 minus 0.42 x by d into fck bd squared, right. Lever arm is given as z equal to d into 1 minus 0.416 into x by d, which can be round off into 0.42. And if the stress is still in if the stress in steel is fst, okay, so it will be a value which is less than the yield stress, because of we divide it by partial safety factor, okay, which is for 1.15 for the case of steel, right. So equating the forces, 0.36 fck into x by d into bd equal to fst ast implies x by d equal to fst ast by 0.36 fck bd, right. So how to now let us see how to calculate the steel area, okay. So we initially have to find out the x by d value, okay, using this, okay. Then we have to find out, so this is basically from the this one, the compression side, okay. So if we know the value of say for example mu d b fck and fy, okay, so how to find out the steel area? So basically we will compute x by d, okay. Then we will use this equation, basically this is equation from the this one side, compression side, okay. So we know the mu, say for example z will be the lever arm, okay, which we will calculate, okay. So for finding the steel area, we can use the equation which is used for calculating the moment carrying capacity from the tension side, okay, which is mu equal to 0.87 fy ast into z, okay. So using this equation, okay, we will be able to calculate the AST value, that is if B, D, MU, FCK and FY values are given, okay. So here we will check whether X by D is less than XU by D, okay. So this is the condition for under reinforced section, okay. Now analysis and design of RC section. So due to concrete failure, as we just discussed, MU equal to K FCK BD square, right. And K is nothing but 0.36 XU by D into 1 minus 0.42 XU by D, right. So for various grades of steel, XU by D values will be differ, and using these values, we can find the value of K, okay, which is 0.149, 0.138, 0.133. We just now discussed this 0.138 FCK BD square, that is for the case of Fe415. Similarly, for Fe250 it is 0.149 FCK BD square, and for Fe500 steel it is 0.133 FCK BD square, okay. All these three formulas are important. Okay, so if possible, write it down separately. So second, from the assumption that steel reaches yield at failure, okay. So if we assume that steel reaches the yield at failure, then we will calculate it using mu equal to 0.87 Fy AST, okay, D minus this one, okay, 0.42 x by uh, this one 1 minus 0.42 x, okay, and substituting we get this equation, okay, AST by BD into Fy by FCK, okay. So using this, okay, it implies that mu equal to 0.87 Fy, okay, and AST is nothing but this one PBD by 100, okay. So P by 100 and BD here into D, it becomes BD square, okay, and this is 1 minus Fy. So this one, the AST by BD, okay, so that will be substituted using I think this equation, okay. So it will be P by 100, yeah. So 1 minus P by 100 into Fy by FCK. So it is a derivation. So given mu, FCK, B and D, this is the equation. We can use it to find x by d, and x by d should not exceed the limiting value, okay, which is basically 0.48 for my this one Fe 415, 0.53 for mild steel, and 0.46 for your Fe 500, right? So the balance steel percentage, okay, PT limit is equal to 41.3 into FCK by Fy into XU by D, okay. These are standard formulas, and the lever arm, as you saw, it is calculated by Z equal to D into 1 minus 0.42 into X by D, right? So which becomes like this. And so these are the basically the formulas and the derivations for the singly reinforced sections, which we discussed basically last class. And this is just a this was just a brief revision, okay. So now let us solve problems, okay. So basically this is a singly reinforced section having three 16 mm diameter bars at the tension side, and the beam is having a width of 250 mm and overall depth of 400 mm, okay. So we need to calculate the ultimate moment carrying capacity of the rectangular beam, okay. So these are the values, and the concrete is of grade M20 and steel of Fe415, okay, and the clear cover is taken as 25 mm. So basically, because it is M20, so FCQ will have value of 20 megapascal, and Fy have a value of 415 megapascal, right? ES, as we all know, is 2 into 10 to the power 5 megapascal, okay. So using this, we can calculate the epsilon SU value from this formula, which comes out to be 0.0038, right? So as you can see here, the strain diagram, so this is 0.0035 and this is 0.0038, okay. So x by d will be nothing like using the similarity of triangles, it will be nothing but 0.0035 by 0.0035 plus 0.0038. So this is how we calculate the x by d value, okay. So using this, we get it is x by d value is 0.48 for Fe415, right? For Fe 500 it will be 0.46, okay, and for Fe 250 it will be 0.53, okay. So everything remains the same apart from this value, okay. So this value is nothing but this equation 0.87 Fy by Es plus 0.002. So this value changes, okay, and according to this value also changes, and you will get 0.46, 0.48 and 0.53 for 500, 415 and 250 respectively, okay. So we've calculated x by d value, which is 0.48. So the balance percentage of steel, okay, a limiting condition, we can calculate it by equating the forces at tension and compression side. So using this equation 0.87 FYSD equal to 0.36 FCK BX, and substituting by D and by P value, so we get P is equal to Fy by FCK, P into Fy by FCK equal to 0.36 into 0.48 by 100 into 100 by 0.87, which is 19.86%, okay. So here for Fy is equal to 415 megapascal, FCK 20 megapascal, which are given. So P becomes 0.957%, okay, which is in the limiting condition. Now let us see what is actually given. So this is the required amount of steel, okay, percentage at limiting condition, but we are given three 16 mm bars, which means area of steel will be 600 mm 603 mm square, which in terms of percentage is 0.657%, okay, which is less than 0.957%, right? So this is less than 0.957%. So this was required for the limiting condition, balance condition, but we are providing it less. Okay, that means the failure will occur at the steel side first. That means it is the beam is under reinforced, which is a good thing, right? So it is a under reinforced section. Okay, and the effective depth is 400 minus 25 minus 16 by 2. This was the clear cover, and was the diameter of bar. Okay, so effective the effective cover basically, subtracting the effective cover from the actual depth, we get 367 mm, right? So this is the effective depth used in this equation. So basically from the area of steel we found that the beam is under reinforced. Okay, so moment due to steel failure. Okay, so because it is under reinforced, so we will be using the moment carrying capacity from the side of tension. Okay, so that means it will be 0.87 fy ast into z. Okay, and substituting ast and z, we will get it as mu equal to 0.87 into fy into p by 100 into 1 minus p by 100 into fy by fck into bd square. Okay, so this is the equation. Substituting Fy as 415, P as 0.657, FCK as 20, and B and D as 250 and 367 respectively. So we get mu, that is the moment carrying capacity, as 68.98 kilonewton meter. Okay. So this is the amount moment carrying capacity with respect to steel. Okay, due to steel failure because it is under reinforced. Okay. If we would have considered the moment carrying capacity due to concrete failure, so again we will use that standard equation, which is 0.36 FCK BD square into x by d into 1 minus 0.42 x by t, right? And substituting the values, we will get the moment carrying capacity as 93.13 kilonewton meter. Okay, so definitely it will be more. Okay, because it is under reinforced section, right? So the moment carrying capacity of steel will be less, which is 68.98 kilonewton meter. Okay, and yeah, so that is what it has been noted here. So moment carrying capacity due to concrete failure is 93.13 kilonewton meter, and same for the steel failure is 68.98 kilonewton meter, right? But the ultimate moment carrying capacity will be taken as the minimum of these two values. Okay, so one is 68.98 and other is 93.13. So as 68 is lesser than 93, so the ultimate moment carrying capacity is 68.98 kilonewton meter. Okay, and that is happening because of the failure of steel. Okay, that is due to under reinforced section. Okay, so yeah, so we will be, this was singly reinforced section, as you can see here. Now later in the coming slides we will be going to flange sections and doubly reinforced section, right? So these are some of the examples. Okay, this is a T beam, this is a where this is basically a slab, and this is the this one, the reinforced beam section. Okay, but this is monolithically constructed. Okay, so if you see here this, you can feel like it is one structure only. Okay, it is although it is two different section, but it is behaving at this part as a single section. Okay, so that is what nothing but the flange section, right? So we'll be discussing in the coming slides, right? So before that, let us briefly go through the doubly reinforced section. Okay, so we just now discussed what is singly reinforced section. Now we will go through doubly reinforced section. Okay, so what is doubly reinforced section? If I briefly simply say, so it is nothing but it is having reinforcement at both the tension as well as the compression side. Okay, in singly reinforced section, the reinforcement was provided only in the tension zone. Okay, but in doubly reinforced section, it will be provided both in the compression as well as in the tension zone. Okay, so here, because of the providing both side reinforcement, some extra parameters will come, such as mu2, ast2. Okay, so in singly reinforced section we only had mu1, ast1. Okay, but in doubly reinforced we will have mu2, ast2, etc. Okay, asc, fsc, etc. Okay, we will discuss all those. So now let us start the design of doubly reinforced beam. Okay, under flexure bending. So yeah, so what is doubly reinforced beam? So the steel reinforcements in both the tension and compression zones are called doubly reinforced beams. Okay, so it is having reinforcement both in the compression as well as in the tension zone. Okay, so as you can see here, it is having AST as well as ASC, that is area of steel in tension and area of steel of area of steel in compression. Okay, so this is equivalent to, okay, the singly reinforced section, okay, which was having only tension reinforcement and of area AST1 plus the doubly, okay, the extra, okay, which is AST2 and ASC. Okay, so it is the combination of AST1 plus ASC and AST2. Okay, so, and as you can see, this is the strain at under compression 0.0035, and under for Fe415 under tension is 0.0038. Okay, so here if you see, the total area of steel in tension is AST1 plus AST2, right? So so basically if you draw the section, it will look something like this. So it will have, as singly reinforced section, it will have AST, which is equal to AST1 plus AST2, and it will also have area of steel in compression, okay, which may be lesser because it is in the compression zone. Okay, so as you can see, this we have discussed earlier also. So now let us see, like basically when is doubly reinforced beam required. Okay, so why it is required? So there may be two reasons, okay, for which the doubly reinforced beam may be required. First is the main reason, when the construction depth is restricted, okay, and the moment the beam has to carry is greater than the moment capacity of the beam in concrete failure. Okay, so as we all know, what is the moment carrying capacity of beam? Okay, so it is basically 0.36 FCK, okay, BXU, right? BXU, or if we see the limiting moment into D minus 0.442x, okay, right? So, or if we say, for example, if we take the limiting moment condition, it is 0.138 FCK BD square, right? So the factor which is mostly influencing is the D, okay, the effective depth, and also B, okay. D, it is square, okay, and B is only linear, right? So this is square and this is linear, okay. So both are proportional. One is directly proportional and one is proportional to the power 2, right? So that means moment increases with the increase in depth and width, right? But there are many cases will be there when the construction depth has to be restricted. Okay, so D has to be restricted, and that is, square. Okay, that is, proper. It is proportional to the power 2. Okay, so if you increase by twice, the moment carrying capacity will increase 4 times, right? So unfortunately, in some conditions, the depth can't be increased as per will. It has to be restricted. Okay, so at that case, okay, the moment carrying capacity, okay, of the singly reinforced beam will be less than the moment carrying capacity which is required. Okay, so it is less, so it will not be able to take the actual full moment carrying capacity desired. Okay, so in that case we have to add extra. Okay, so then therein comes the concept of doubly reinforced. That is one condition, and the second condition is when the bending moment at the section can change in sign. Okay, so for example, it can be due to some moving load or even due to some cyclic load. Okay, so say for example, if you say in this, say for example, this is a some road, okay, and it is having or say some bridge, okay, it is a bridge which is having support here at 4 points only, okay, and here there is no support. Okay, so this is a vehicle, say for example. So if you see here, when the when the vehicle reaches this point, okay, here if you see the beam here, okay, so this will be something like this. Okay, so it will undergo sagging. Okay, so sagging means the upside portion will be under compression and the downside portion which will be under tension, which is why we designed the singly which is how we design which is for this is the case for which we have designed a singly reinforced section, right? So the just contact zone is the compression, and the below zone is the downward zone is the tension. Okay, so that is the case for which we have designed. But whenever the car will move from this point to this point, say for example this point, okay, so this portion will start behaving in a hogging manner. Okay, so it will undergo sagging here, but it will undergo hogging. Okay, so that means the upside portion will be under tension and the bottom portion will be under compression. But if we have not designed it for doubly reinforced, so there will be no tension carrying capacity of the beam under in the above portion, because it is completely in concrete, right? So that will also not be able to withstand this load, right? Because it is a moving load. Okay, one time it will be under compression, the other time it will be under tension. Okay, so because of the hogging sagging thing. Okay, so these two conditions basically, when firstly when the construction depth is less restricted, and secondly when the load is moving. Okay, so the section can change its sign. Okay, so at both these conditions the doubly reinforced beam is required. Okay, so now let us see how the analysis of doubly reinforced section is carried out. So for this, there are some basic considerations we have to take into account. Firstly, the reinforced concrete section in bending fail when the compression strain in the concrete reaches the value 0.0035. So this is a constant value. Okay, the extremmost fiber in compression has a strain value of 0.0035. And second condition is plane section remains plane even after bending. Okay, so this is also important condition which which allows us to assume that the strain, okay, the strain happening through the section is linear. Okay, if this condition is not it is not it is not supported, then it will be not linear, so that will not help us to uh, you know uh, derive the equations, required equations. So firstly 0.0035 is the maximum strain at the extreme fiber in compression, and secondly plane section remain plane even after bending. So these two considerations are taken, and apart from that also we take into consideration the stress at any point in steel and concrete can be taken as equal to the stress corresponding to the strain at that point of the stress strain graph of the material. Okay, so at any point if we require a stress, okay, so that will be equal to the corresponding stress, like that stress will be equal to the stress corresponding to that strain, particular strain occurring at that point. Okay, and that value can be found out from the stress strain graph for the given material. Okay, so this condition is basically important for finding the FSC value. Okay, FSC is basically the strength of steel in compression. Okay, at that point, okay, where the rebars are there at the compression side, so that value FSC, it has to be found out using the epsilon SC value. Okay, and that epsilon SC will be less than the epsilon SU value, which was uh, the outermost fiber in tension. Okay, the strain value at outermost fiber in tension, so that was having a value of 0.87 fy by es plus 0.002, right? So that was the maximum value, but that this epsilon SC value, it will be lesser than that. Okay, so based on that point, okay, based on that point from the stress strain graph for that particular strain, we have to find out the stress, okay, for the steel at compression, which is FSC. So for this, this condition is consideration is required. Okay, so now let us start. Okay, so if you see the doubly reinforced beam sections, okay, we will analyze now. So for if you find out the doubly reinforced beam sections, so you will see that like the basic things are almost same, like this is the compression extreme fiber in compression. Okay, the strain value is 0.0035, and extreme fiber in tension, the strain value is epsilon S or SU, right? But some things, new terms have come up, such as D prime. Okay, so D prime is basically the cover, okay, the effective cover from the compression side. Okay, so effective cover from the compression side, so that is basically the D prime value. Okay, and also you will find that there are two lever arms present. Okay, so one is the ZC value, z that is ZC is was basically the distance between the center of compression of concrete and center of tension of steel. Okay, so that was the ZC value, but now one more term has come. Okay, that is ZS. Okay, so that is the center of distance between the tension and compression reinforcements. Okay, so ZC was equal to D minus 0.42x, right? However, ZS will be little different. It will be equal to D minus D prime. Okay, so for finding the moment carrying capacity from the side of concrete. Okay, so we have to use both the ZC value as well as the ZS value. Okay, but for finding the moment carrying capacity from the side of steel, like from the side of tension, it will be one only. Okay, So it will be 1. We will assume one value only. Okay. So we will find out when we solve problems how it is done. Okay. So yeah, so d prime is equal to basically clear cover plus 5 by 2. Okay, so that is the effective cover from the side of compression. Okay, so C is equal to total force in concrete, which is equal to CC plus CS. Okay, so CC we discussed while starting only. So we just K FCK BD square, right? So this is 0.36 x by d into 1 minus 0.42 x by d, and for limiting condition this value comes to be 0.138 for Fe415, 0.133 for Fe500, and 0.149 for Fe250, right? So these were the values. Okay, and yeah, so yeah, so that was CC, and now here there is one more term which is CS. Okay, so that is CC into ZC plus CS into D minus D prime. So this is the CS is the force due to steel in compression, and CC is the force due to concrete. Okay, so yeah, so this is the equation. So if you see here, so this is the epsilon SC value. Okay, so if we try to derive, okay, so if we try to derive, we will find that epsilon SC from similar triangles. If you derive, we will find epsilon SC equal to 0.0035 into 1 minus d prime by x. Okay, and if we consider x max equal to d by 2 or 0.5 d, we will find 0.00335 into 1 minus d prime by 0.5 d should be greater than equal to 0.002. Okay, so for so that this is present above a above the this one 0.002 strain, like after that this is constant, right? So to be present in a region which has a constant strength, okay, concrete strength basically, so we try to always keep the location of the reinforcement in compression at a strain which is greater than 0.002. Okay, so that is a concept. So basically that is for two reasons. One is so that the concrete also have substantial strength along with reinforcement at that section, and secondly to ensure that the reinforcement is particularly in the like the maximum compression zone. Definitely the region between 0.002 to 0.0035 will have the maximum compression, right? So that's why for these two reasons we always try to keep it greater than equal to 0.002. Okay, so like solving this, we find that d prime by d should have a value of less than equal to 0.214 or zero point 0.2. Okay, so that is the ideal case. Okay, so like using this material curves. Okay, so this is a stress strain curve for cold work deformed bar. Okay, so similarly for type of rebar we are using, so using the stress strain curve, we basically try to find out the strain, the strain and the stress values. Okay, so basically strain and stress values are found out using the typical the stress strain curve. Okay, so here basically for example, uh, 0.87 Fy is the yield strength. Okay, we take partial factor of safety as 0.87, but that is 1.15, so we get 0.87 Fy. So say for example we have plotted various values. Okay, zero point 0.8 times 0.87 Fy, 0.85 times 0.87 Fy. Okay, like this 0.9, 0.95, 0.975 and 1. Okay, so these values will be basically this one. Okay, so if you calculate, say for example 0.8 into 0.87 into 415, okay, so you will get a value of 288. Okay, similarly if you calculate 0.95 into 0.87 into 415, okay, so you will get a value of 342. Okay, so like this stress value is found out. Okay, and for this corresponding stress, okay, like from design stress strain curves we find the corresponding strain. Okay, so definitely this will be 0.0038, that is from the ultimate value only. Apart from this, these values are found out from the design stress strain curves for the particular the this one rebars. Okay, type grade of rebars. Okay, so this is the design stress strain curve. Okay, so these are the values obtained from the design stress strain curves, which will be used for finding the FSC value for a given epsilon SC value. Okay, so we will we will understand when we solve problems. Okay, so yeah, so the analysis of the beam. Okay, so how it is done for the doubly reinforced. Okay, so we will follow the concepts of singly reinforced only. Okay, so that is what firstly we calculate the mu, okay, for concrete failure as a singly reinforced beam. Okay, and that is in the limiting condition, because we definitely know that the moment which we require will be greater than the limiting condition, right? So we directly go for the limiting. Okay, so limiting for Fe250 is 1.148 FCK BD square. For 415 it is 1.13 FCK BD square. For 500 it is 0.133 FCK BD square, right? So after that we determine the balance steel required. Okay, so which we did for the singly reinforced also. So this is 0.87 Fy AST equal to 0.36 FCK BXU equal to implies AST by BT equal to 0.36 by 0.87 into FCK by Fy into XU by D, right? So XU by D values are this, and PT values are using this equation, and this we find this. Okay, so this all we have discussed just now in the starting slides. So using this, okay, we try to determine the stress in compression steel. Okay, FSC value. Okay, so FSC value is found out. Okay, so we try to say, for example, for M20 0.45 FCK will be 9 Newton per mm square, and 0.87 Fy is 361 Newton per mm square, right? So say for example these are some certain values. Okay, so from that we, and from the values we try to find out basically the epsilon SC value based on the location, and from that we try to find out the FSC value. Okay, so CS equal to FSC ASC apart from these values. So we'll solve problem now. We will find out how it is done. Okay, so first we try to find out mu1, then we try to find out mu2. Okay, so mu1 was basically the singly reinforced capacity. Okay, so moment carrying capacity on the singly reinforced section. So that was always less than the required. Okay, so the additional moment in compression failure, okay, due to compression steel. Okay, so that is equal to mu2. Okay, so this mu2 is equal to FSC ASC into D minus D prime. Okay, so yeah, so that is the basically the this one the extra moment carrying capacity in terms of compression side. Okay, compression failure. And this AC is area of compression steel, FSC is stress in compression steel corresponding to its strain. Okay, from based on this we try to find the FSC value, right? So after that, we try to find the total mu for concrete failure, which is equal to muc equal to mu1 plus FSC ASC into FSC AS into D minus D prime. So mu1 is basically the same for the concrete as well as steel, right? Because it is under limiting condition. This value is the additional moment carrying capacity, okay, for the doubly reinforced section. Okay, so this is the total mu for concrete failure. Okay, similarly for tension failure, okay, we have to find out the extra area of steel we have provided, which is AST2. Okay, so that is equal to the total area of steel minus the area of steel for the singly reinforced. Okay, so find total mu for tension failure considering final failure to be done to tension steel reaching yield. Okay, so this will be mu will be mut. Okay, so mut equal to mu1, as I just told you, both will be same because it was in the limiting condition, plus AST2 into 0.87 Fy into D minus D prime. Okay, so here it is FSC ASC into D minus D prime, and here it is AST2 into 0.87 Fy into D minus D prime. So that means FSC into AS, okay, ASC is equal to AST2 into 0.87 Fy. Okay, the only problem is we have to find out the FSC value. Okay, so that is found out from epsilon SC. Okay, so we will find out how it is done. So finally we get the total mu for concrete failure and total moment due to tension failure, steel failure. Okay, so therefore the total moment carrying capacity of the section will be minimum of muc and mut. Okay, we always take the minimum, so that will ensure the overall safety, right? So the total moment carrying capacity of the concrete of the RCC doubly reinforced section will be minimum of moment carrying capacity due to compression and due to tension. Okay, so yeah, so basically this is all about this is about what we discussed. So initially we tried to find out the mu1, which is kfck bd square, k having 0.133, 0.138 and 0.149 value, right? Then we calculate AST1 from the expression for balanced section. Then we try to find out the mu2 value, which is equal to mu minus mu1. Mu is the desired value, okay, which will be provided, will be given in the question. Then we try to calculate the AST2 value, okay, which is equal to mu2 by 0.87 into Fy into d minus d prime, right? So like this we will get the AST2 value, okay, AST2, okay. Then we calculate the total steel area in tension, which is AST equal to AST1 plus AST2, right? Then we try to find the stress in compression steel, okay, FSC, using epsilon SC, okay. So epsilon SC is equal to, if we from the strain diagram, it is equal to 0.0035 into 1 minus d prime by x, okay. So using this we try to find the epsilon SC, and from that we try to find the FSC, okay. And this is the relation ASC equal to AST into 0.87 Fy by FSC, okay. So we find the area of steel in compression, okay. So this was all about how to design the doubly reinforced section, okay. So now let us apply the concept and try to solve this problem, okay. So analysis of doubly reinforced beam, okay. So say for example this is the beam, okay, which is having a width of B 300 mm and total depth has 500 mm, okay, and clear cover is 25 mm, and concrete is having a grade of M20 and steel of grade Fe415, okay. In the compression side, the reinforcement we are providing 320 diameter bars, and in tension side we are providing reinforcement of 525 mm diameter bars, okay. So what is the moment carrying capacity of the doubly reinforced section, right? So what we will do is we will find initially the limiting moment carrying capacity, okay, assuming it to be a singly reinforced section, right? So since it is Fe415, okay, so the limiting moment will be 0.13 FCK BD square, okay. If it was Fe500, it was 0.133 FCK BD square, and if it is Fe250, it is 1.149 FCK BD square, right? So FCK we know, right, 20, B we know it is 300, and D we have to find out, which is equal to actual depth, that is 500, minus clear cover, that is 25, minus 25 by 2, okay. 500 minus 25 minus 25 by 2, which is 462.5 millimeter, okay. So substituting these values, we get mu1 value to be 177 kilonewton meter, okay. Now secondly we will try to compute the balance steel, okay. So we will use again the expression for we'll equate the forces of in tension and compression, considering it to be singly reinforced, right? So we'll see which is present in area of 0.87 FYST equal to 0.36 FCK BXU, and then we will try to substitute AST by, that is area of steel, by BD with PT, okay, and we will get the relation PT equal to 0.36 by 0.87 into FCK by Fy into XU by D into 100, right? So using this relation and substituting the values, we will get PT value as 0.957 percentage, okay. And yeah, so this is the amount of this one steel at limiting condition, okay, because we have considered XU by D value as 0.48, okay. So that is the limiting condition, so PT value is 0.957%, okay. And now based on this we will we are all we have assumed this based on the singly reinforced section criteria, as I just told you. So basically we will try to find out the AST1 value, okay. So AST1 value was the this was actually, this is the total area of steel provided, okay. So based on we will find what is the area of steel for the singly reinforced section and what is the additional area of steel required, okay. So AST1 will be calculated from the limiting this one limiting percentage, which is PT by 100 into PBD by 100. So using substituting the values, we get the area of steel as 1328 mm square, okay. But we have provided AST value, area of steel, as 5 into pi by 4 in like 525 mm bars, right? So that is equal to 2454. It is higher than the AST1, okay. So the additional extra area of steel provided has been 2454 minus 1328, okay, which is 1126 mm square. So this is the extra, okay. This was for the singly reinforced area of steel, okay, section area of steel, and this is the extra amount of area of steel that is provided, okay. So that is the, using this we will be able to find out the mu2 value, okay. So mu2 value is how much? So it is AST2 into 0.87 Fy into D minus D prime, okay. So therefore AST2 value will be 1126, as you can see. Fy is 415 and d minus d prime is 462.5 minus your this one 25 plus 20 by 2, that is 35. Okay, so yeah, it is mentioned here. So d prime is clear cover plus 5 by 2, 35 mm. Okay, so substituting the values, we get mu2 value as 173 kilonewton meter. Okay, so what is the total moment carrying capacity? It will be, so it will be nothing but the sum of singly reinforced moment plus the additional steel moment. Okay, so that is mu1, which was 177, plus mu2, which is 173. So 177 plus 173 is 350 kilonewton meter. Okay, so that is from the tension side. Okay, now we will go through the compression side. Okay, so let's see the, yeah, for the compression side the mu1 value will be the same, that is 177, because that is the limiting condition, right? So it is a balanced condition, so it will be same for both tension and compression. It is 177. What we will try to find, what is the mu2 value for compression. Okay, so for that we will see use the compression steel. So d prime is 25 plus 20 by 2, 35. Okay, so d prime by d is 0.0756. Okay, so yeah, so xu by d is 0.48, right? So xu, it will be 222 millimeter. Okay, so because that is the maximum, okay, maximum value, so we have to always take maximum xu by d 0.48. Okay, then only limiting condition mu1 value will come, right? So it will be definitely 0.48. So xu is 222 mm. So from the similarity of triangles, w epsilon sc will become 0.002948. So that is the uh, strain. Okay, strain at the position of the compression reinforcement. Okay, so that is 0.002948. So this table which we discussed earlier, so using this table we will try to find out, okay, from through interpolation, the value of FSC, that is stress in steel at compression, at a strain value of 0.002948. So if you see clearly, it will be between these two values. Okay, these two values. So at 0.00276 it is 351, and at 0.0038 it is 361. So what will be the FSC value at 0.002948? So this we have to find in between 0.002948. So using, as you can see here, the values have been given. So using the linear interpolation, we will try to find, and we get the value as FSC as 352.8 Newton per millimeter square. Okay, so this is the stress in steel at compression for a strain value of 0.002948. Okay, so the FSC value is 352.8 Newton per mm square. So using this, we will be able to find out the mu2 value. Okay, which is equal to FSC into ASC into d minus d prime, right? So FSC value we got 352.8. Okay, ASC value we can calculate 3 into pi by 4 20 square, because 3 20 mm bars, right? So it is 942, and d is 462.5, and d prime is 35, right? So using this only, we get the value of mu2 as 142 kilonewton meter. Okay, so if you remember, here we got the mu2 value in the tension side is 173. Okay, it is higher, but in compression side it is lower. Okay, 142 kilonewton meter. So if you see for this one, for concrete, the total moment carrying capacity will be 177 plus 142. Okay, so this is 177, which was constant, right? 177 was constant. So this was 177 plus 173 in tension, and here it is 177 plus 142. Okay, in compression, which is becomes 390. Okay, so from tension side we got total moment carrying capacity is 350 kilonewton meter, and from compression side we got the total moment carrying capacity of 319 kilonewton meter. Okay, so therefore the moment carrying capacity of the section, doubly reinforced section, okay, so that will be minimum of 350 and 319. Okay, which is basically 319 kilonewton meter. Okay, so this is how we have to solve the problems. Okay, so let us try one more problem. So design of doubly reinforced section. Okay, so we need to design basically. So here mu is 350 kilonewton meter. So this is the required or desired moment carrying capacity. The grade of concrete is M20, grade of steel is Fe415. Okay, width is 300 mm, and the restricted depth is actual depth 600 mm. Okay, So these are the values given. Clear cover is 25 mm, and let us assume the diameter of rebar is 25 mm. Okay. So these are the values we have been given. We need to design the reinforcement. Okay. We have to design the section. Okay. So how will we proceed? First, we will try to find out the effective depth D, which is equal to capital D minus clear cover minus half diameter, right? So it is 600 minus 25 minus 25 by 2, okay, which is 562.5 millimeter, okay. Then we will try to find out the limiting capacity, moment carrying, which is for 415.138 FCK BD squared, right? So this comes out to be substituting FCK is 20, BS 300, and DS 562.5, we get Mu1 as 261.9 kilonewton meter, okay, which is much less than the desired moment carrying capacity, okay. So that means we have to go for doubly reinforcement, okay. So now what we will see is the balance steel, okay. So that will be used for finding the AST1 value, okay. So balance steel PT is 19.82 into FCK by FY, okay. So FCK is 20, FY is 415, we get 0.955%, right? So therefore AST1 should be how much? It will be 0. It is PBD by 100. Okay, so 0.955 into 300 into 562.5, right? Yeah, by 100. So it becomes 1611 millimeter square. So area of steel in tension for singly reinforced, it is 1611 mm square. Okay. So now using this, okay, we will be able to calculate the AST2 value and from the Mu2 value. Okay, so initially we have to find out the Mu2 value. So that will be nothing but 350 minus 261.9. Okay, so assuming it is 262, it is Mu2 value becomes 88 kilonewton meter. Okay, and here they have let us consider the compression rebars as 20 mm. Okay, so the tension rebars we have assumed as 25 mm, yeah, and compression let us assume is 20 mm. Okay? So AST2 is basically mu2 by 0.87 fy into d minus d prime. Okay, so for d prime the value will be 25 plus 20 by 2, okay, because this is 20, so it becomes 35 mm, right? So substituting these all values, okay, we get the AST2 value as 462 millimeter square. Okay, so the total tensile steel which will be required is AST equal to AST1 plus AST2 equal to 1611 plus 462 equal to 2073 mm square. Okay, so taking n, okay, into pi by 4 into 25 square, okay, equal to 2073, we can find the value of n, that is the number of tension rebars required, okay, reinforcements required. So therefore the T2 value, okay, the tension force from the AST2 value, okay, so that will be additional steel value, the tension force due to the additional steel, okay, that will be equal to AST2 into 0.87 into Fy, which is equal to 462 into 0.87 into 415, okay, so that becomes 166.805 kilonewton, okay. And if you compare, ASC is equal to T2 by FSC, okay, equal to CS by FSC, okay. So that is nothing but ASC into FSC equal to 0.87 Fy into AST2, okay, we just discussed earlier. So yeah, so now we have to find, so we have designed the amount of tensile steel that is required, okay, so that is 2073 millimeters square. Okay, now let us go for the compression side and find out the amount of steel they are required in compression. So here we will get the XU value as 270, that is 0.48 into 562.5, so it becomes 270 millimeter. So the epsilon SC value, okay, so using the similar triangle concept, okay, so we will find out that the epsilon SC value will be it is 1 minus d prime 1 minus 0.0035 into 1 minus d prime by x, okay, so that is 0.0035 by 270 into 270 minus 35, or 0.0035 into 1 minus 35 by 270, right? So that will be equal to 0.00304, okay. And using this values from design stress strain curve, okay, we calculate the FSC value for a strain value of 0.00304 using interpolation as 353.7 megapascal, okay. So using so we found out FSC, okay, so we know AST2, Fy and FSC. So using these values we can find the area of steel in compression. Okay, so if we calculate, it comes out to be 471.16 millimeter square or 471 millimeter square. So therefore, the amount of steel in tension, okay, is equal to 2073 millimeter square, and the amount of steel in compression, that comes to be 471 millimeter square. Okay, so now, so this is all about basically the doubly reinforced section. Okay, so now let us go to the third topic, which is the design of flange beams. Okay, so these are some of the parameters which is required. This is the width of flange, this is total depth, this is depth of flange, this is depth of web, this is width of web. Okay, so we'll discuss in the coming slides. So let us start then. So basically, flange section is nothing. It is a, like, basically, and some extending part is there, okay, in the beam, okay, which is basically from the slab, okay, when they are monolithically cast together. Okay, so it acts as a one unit, although it is basically two. Okay, and that is mainly used for re-strengthening the member. Okay, adding additional strength. So this can add some additional strength. Okay, so because of that, it is used. Okay, so here, as we discuss, there are various, we can name the various portions. Okay, so this is the web, this is basically the web. Okay, and this is basically the flange. Okay, so this is the width of flange and depth of flange, and this is the width of web and depth of web. Okay, and as we discussed earlier, this is the effective depth and this is the actual depth. Okay, so this is a T beam. Okay, similarly this is a L beam. Okay, so it is also flange beam, but it is mainly present at the corners. Okay, because corner there will be no basically edges. Okay, so at edges there will be no this side. Okay, so it will end here. So there's like this, beams will be found there when slab is cast monolithically. So that is the L beam. Okay, so this is a T beam, this is the L beam. Okay, so as per clause 23.1.1 of IS 456, okay, a slab which is assumed to act as compression flange, okay, of T beam or L beam shall satisfy the following criteria. One, the slab shall be cast integrally with the web, okay, and the slab shall be effectively bonded together in any other manner. So that is possible either if we directly cast a beam, okay, having a shape of T, okay, so that is possible then. Okay, that is, it is having flange as well as web, or otherwise, if we are casting slab with a beam, okay, either we are casting a beam which is of T shape, which is very rare, or we are casting a beam as well as a slab together. Okay, so then also it becomes a T beam. Okay, so that is a criteria. And secondly, if the main reinforcement of the slab is parallel to the beam, this in reinforcements, okay, so the transverse reinforcement shall be provided as shown in the figure, and this reinforcement shall not be less than 60% of the main reinforcement at midspan of the slab. So if this is the main reinforcement, okay, at the this one main at the uh, midspan. Okay, so at the midspan, so if this is the main reinforcement at the midspan, transverse reinforcement should not be less than 60%. Okay, so these are some of the criteria we have to take into account while designing of T beams or flange beams. So yeah, so as I just discussed, these are the locations of T beams and L beams. Okay, so this L beam you will find in mainly in the edges, okay, edges of a building, and this T beam you will find in the interior. Okay, so interior sections anywhere. Okay, because it is present both side, but here it is only present right side, not left. Okay, so yeah, so these are some of the formulas which can be used for finding the effective width of flange. Okay, so yeah, for T beams, okay, so effective width is equal to L naught by 6 plus BW plus 6DF. Okay, whereas for L beams, it is BF equal to L naught by 12 plus BW plus 3DF. Okay, so L naught is basically the length of the beam. Okay, so it is the length of the beam, and that is mainly the region. Okay, the region till where the moment at the beam is zero. Okay, so zero moment locations. Okay, the distance between two zero moment locations. Okay, so that is basically the length of the beam. Okay, that is considered to be the length of the beam, L naught. Okay, so BF equal to L naught by 12 plus BW plus 3DF. Okay, for L beam, and for T beam it is L naught by 6 plus BW plus 6DF. Okay, In a case of isolated beam, okay, so only one beam is there, so that is isolated, it is not connected as shown here, okay, this is not isolated, okay. So if it is an isolated beam, so the effective flange width shall be obtained as, for T beam it will be BF equal to L naught by L naught by B plus 4 plus BW, okay. For L beam it will be 0.5 L naught by L naught by B plus 4 plus BW, it will be half, okay. So these are some of the equations for calculating the width of flange, okay, for isolated as well as non-isolated beams, both for T beam as well as L beam, okay. So now here, uh, in order to in order to design, okay, so in order to design there are three cases that will emerge, okay. So three cases, for the three cases the design will be different, okay. So first case is that the neutral axis or NA that will lie within the flange, okay. So neutral axis will lie within the flange, so like this, okay. So it will end within the flange, okay. So if that is the case, okay, so if that is the case, so we will see what happens if that is the case. So first is that the neutral axis will lie within the flange. Second is the neutral axis will not lie within the flange, it will lie outside the flange, but it will be uniformly stressed till the flange, okay. So it will be something like this and then like this, okay. It will be straight up till flange and then it will reduce, okay. So it will be below the flange, but the flange will be uniformly stressed, okay. And the third case is, so okay, so if it is in the second case, if it is uniformly stressed, so you can see, okay, so there will be a rectangular part, okay, which is the beam, basically this beam web, okay. And there will be the extra flange part, the extension, okay. So which is equal to BF minus BW, because we have considered here only the BW, okay. So it will be BF minus BW, okay. So here because it is uniformly stressed at this portion, it will be 0.45 FCK, okay. So that is the second case. And in the third case, what will happen? Again, the neutral axis will be present below the flange, okay. But the flange will not be uniformly stressed, okay. So the reduction will start inside the flange only, okay. So it will be not constant throughout, okay. After a certain portion, it will start decreasing, okay. So the flange is not uniformly stressed, okay. So these three conditions are different, okay. So let us see how it will be, varying, okay. So initially, so let us see, uh, yeah. So if we consider, okay, if we consider that the neutral axis, okay, so the neutral axis, sorry, if we consider that the flange is uniformly stressed, okay, neutral axis will definitely be below the flange, okay. But if we consider that the flange is uniformly stressed, okay, so that will be only possible when the depth of flange will be less than equal to the strain of 0.002, right? Because after 0.002 from the concrete diagram we find that the stress is constant, okay. Okay, more than that it is constant, less than that it takes the shape of parabola, okay. So to ensure that the depth of flange will have a constant this one stress, okay, or it will be having uniformly stressed, so it should be less than equal to 0.002, okay. So using that relation and from similarity, okay, we find that df by d value, that is the depth of flange by effective depth, should have a value of less than equal to zero point 0.2, okay. So if it is this ratio is less than equal to 0.2, that means the flange will be uniformly stressed, okay, right. So that is the second case we talk about, okay. So now let's see how the design concepts are varying, okay, for the three cases. So the first case is that, so like before that I want to say is, so from this equation only you can find understand, like if the df by d value is less than equal to zero point 0.2, that means the depth of flange is the smallest, okay. Then the second case will occur, that is neutral axis, okay, will be this one, df, yeah. So if the df by d value, yeah, if the depth of flange is less, very less, then the less than zero point 0.2 it will be the second case, okay. So the flange is uniformly stressed, okay. if the df by d value is more than 0.2. Okay, if df by d value is more than 0.2, then the third case will occur, that is the flange is not uniformly stressed. Okay, and if df by d value is very high, okay, very high, so it is like near, like say greater than 0.5. Okay, so then I think this one, the first case will occur. Okay, that is everything will happen inside the flange only. Okay, so it is less than zero point 0.2, greater than zero point 0.2, and very much, and higher than zero point 0.2. So similar, based on that, case 2, case 3, and case 1 will occur simultaneously. Okay, so now let us see in detail, okay, how we approach the design. So for the first case, the neutral axis will lie within the flange. Okay, so that is when that this df by d value will be quite high. Okay, so at that case, it will be simple. Okay, it will be simple as the design of beam will follow. Okay, simple design of beam, we just need to convert the b with bf. Okay, so it was width. Okay, initially width of beam, now it will be width of flange, because everything is happening inside the flange only, so we can consider this itself to be a beam. Okay, so we can consider this as a beam only and design. So the mu will be 0.36 fck x by d into 1 minus 0.146 0.416 into x by d into bf d square. So when the cross section of the beam only is given, so yeah, so x will be equal to 0.87 fyst by 0.36 fck bf. Okay, where x by d will be this one. Okay, 0.87 fyst by 0.36 fck bfd. So that is the simple. Okay, so it is like designing a beam. Okay, so simple beam when the neutral axis is within the flange. Okay, or the df by d value is quite high, so then we just have to convert b into bf, and everything rest will be same. Okay, the second case. Okay, so this case is when the neutral axis is below the flange and flange is uniformly stressed. Okay, so that is df by d is less than 0.2. So in this case, we have to separate the two parts. Okay, one is the web and other is the flange. Okay, so for the web we will be designing normally as we design, but for the flange, okay, so because it is stress uniform, it is constant, so the 0.36 will become 0.45. Okay, so that is the difference, otherwise it is all same. So yeah, and it will be bf minus bw. Okay, and there also this will be d minus df by 2 because it is constant, right? So it is d minus df by 2, the lever arm. Okay, so mu equal to mu1, that is for the rectangle, bw into d, and plus mu2, which is for the slab. Okay, so mu1 will be 0.36 fck bwx into d minus 0.41x, and mu2 will be 0.45 fck into bf minus bw into df into d minus df by 2. Okay, so that is mu, which is the sum of both the rectangle for considering the beam as well as the slab. Okay, so that is the second case. And third case, okay, when the neutral axis is below the flange but df by d value is greater than 0.2, then the flange is not uniformly stressed. Okay, so there what happens, there comes a new term. Okay, we coin a new term yf, which is equal to 0.15 x plus 0.65 df. Okay, so in this case, okay, we consider that the stress, as here the stress was constant up till df. Okay, because flange is uniformly stressed, we consider here that the flange is constant, the stress is constant up to the depth of yf, not df. Okay, instead of df we have coined a new term yf, and we assume that the stress is considered uniform up to this depth, that is the stress is constant, 0.45 fck will be up till this depth, we assume that. Okay, and by trial and error we try to find the actual depth. Okay, so we will see how it is applied. Okay, so let us see the first problem. So yeah, so let us take this question. So we need to analyze the T-beam. So the width of flange is 1000 mm. The the this one depth of flange is 125 mm, right? The width of web is 250 mm, and actual depth is 400 mm, right? Area of tensile steel is 525, and steel is 5 Fe415, concrete M30, clear cover 25 mm, right? So assuming tensile steel yields, okay. So we need to find out the capacity, right? So assuming tensile steel yields, okay. So we'll find the x value, okay, and that comes out to be how much? That comes out to be 52.48 millimeter, okay. So the neutral axis comes out to be 52.48 millimeter. Okay, so that means we have considered this to be a initially we go to case 1. Okay, so case 1, for case 1 we took the B value as BF, right? FCK was 30, FY 415, BF 1000, and AST is given as 520, okay, 20 bars. So it is 1570. So using these values we got 52.48, and that was that depth is less than the depth of flange, which is 125 that means it is case 1. Okay, so if it is case 1, it is very easy. We just have to for utilize all the concepts derived from beam. Okay, so the lever arm depth will be Z equal to D minus 0.42x. D is how much? D is yeah, D is 365. Okay, 400 minus 25 minus 20 by 2, right? Yeah, 365 mm. So 365 minus 0.42 into 52.48, right? So it is 342.95 mm. So therefore moment of resistance due to concrete failure mu is 0.36 fck BF into X into Z, right? So that is the standard formula. We just substituted B with BF, right? So it is equal to 0.36 into 30 into 1000 into 52.48 into 342.95, which comes to be 194.378 kilonewton meter. Okay, so that is mainly from concrete failure, and from steel failure, so it is 0.87 FY ASTZ as we know. So it is equal to 0.87415 into 1570, yeah, into 342.95. Okay, so it comes to be 194.4 kilonewton meter. So almost both are same. Okay, both are from both sides it is almost same, right? So yeah, so we can say that it is this one almost a balanced section. Okay, so yeah, so the moment carrying capacity it is 194. Okay, so 194.4 kilonewton meter. Okay, so from both sides, concrete as well as steel, we have got this. Okay, so now let us go to the second problem. Okay, so again we need to analyze a T-beam which is having a width of flange 600 mm, depth of flange 125 mm, width of web 250 mm, actual depth 450 mm, area of steel 425 mm die bars, steel Fe415 grade, concrete M20 grade. Okay, and let us assume clear cover as 25 mm. Okay, so the effective depth D. Okay, so it is equal to capital D minus clear cover minus half diameter. That is 450 minus 25 minus this one 25 by 2. So it is 412.5 millimeter, right? So df by d, okay. So it is this one 0.303, okay, which is greater than zero point 0.2, right? So depth of flange given was, yeah, 125, and D was 412. Yeah. So this is 0.303, which is greater than zero point 0.2. Okay. So similar. That means this case, from this case only we know that case 2 is not this one. So case 2, it is not case 2. Okay. So case 2 is rejected. It will be either case 3. Okay. It will be either case 3 or case 1. As I told you, if it is less than zero point 0.2, it is case 2. If it is just greater than zero point 0.2, it is case 3, and if it's very high than 0 0.2, it is case 1. Okay, so we need to find out which whether it is case 1 or case 3. If it is case 3, we will be using YF instead of DF. Okay, so that is it 1 or 3, we will find using the value of X. Okay, that is the neutral axis. Okay, so assuming that the neutral axis lies inside the flange only, so we take BF. Okay, so we'll find out using the equation 0.87 Fy, like equating the forces, we get X equal to 0.87 Fy AST by 0.36 FCK BF. Okay, so Fy is 415, AST is how much? 1964, right? Yeah, and FCK is 20, right? Yeah, and BF is 600, right? Yeah, so from this we get X value is 164 millimeter. Okay, but the depth of flange is only 125 mm. Okay, so it can be 164 mm. Okay, so that means this is the X value. Okay, that is the neutral axis. It is not within the flange. That means case 1 is also gone. Okay, it is rejected. So it is definitely case 3. Okay, so first we will see whether it is case 2. Okay, and if it is less than zero point 0.2 it is yes, if it is greater than zero point 0.2 it can be case, it will be either case 1 or case 3. So for that we will find x. Okay, so df by d is used for finding whether it is case 2, okay, or not, and x is used for finding whether it is case 1 or case 3. Okay, so x will only, we have to only go for this if we are sure that it is greater than zero point 0.2. Okay, so if, since it is greater than zero point 0.2 it is not case 2, so we have tried to find out x neutral axis, and because it is greater than 125 that means it is case 3. Okay, so now, so that also means that this value is wrong. Okay, so this we have to calculate again the neutral axis. So for this we will be using the trial and error. Okay, so first we will assume that because it is 164, so let us assume that x value is 180 mm. Okay, so using taking value of x as 180 mm, the depth of flange is 125 mm, yf value is calculated as 108.3 mm. Okay, now we will equate the forces again. Okay, and in case 3 what we did, if you remember, we took this wave as different and the flange as different, right? So and we assume that up till yf the value will be the stress value will be constant of 0.45 fck. Okay, so equating that we will get x into 0.36 into fck into bw plus 0.45 into fck into bf minus bw into yf equal to 0.87 fy ast. Okay, so using this we find that x value will come to be around 204 mm. Okay, but we assumed it to be 180 mm. Okay, so that means 180 and 204 are not coming equal. Okay, so it is not close also, so that means our assumption is, this assumption is also wrong. Okay, and also we found that this x value will be somewhere near to 204, that will be around 200 mm. Okay, so it will be near 204 mm. Okay, so this assumption also we have to leave. Okay, so therefore let us take the third assumption, let us assume it to be 200 mm only. Okay, so from every x value we will get a near proper like more accurate x value. Okay, so this is an iteration. Okay, so using trial and error you took an x value, you found out where the actual location is, and in the second step you you have taken a much better accurate x value. Okay, so as much as you increase the iterations, the closest x value will be found. Okay, so now we have taken the x value as 200 mm, so from that we have found the yf value as 111.3 mm. Okay, so now performing everything as before, so x into 0.36 into 20, right, into 250 plus 0.45 into 20 into 600 minus 250 into 111.3. Okay, so the equal to 0.87 into 415 into 1964. Okay, so you solving this we find the x value as 199.2 millimeter. Okay, and that is close to 200 mm which we assumed. Okay, so that means this x is correct. Okay, so using this x, okay, we will find the moment capacity by taking moment about steel. Okay, so we will go from the concrete side. Okay, so mc1 will be 0.36 fck bwx, okay, into this one d minus 0.42x. Okay, that is the basically the lever arm. Okay, so that is mainly from the web part. Okay, so from the web part we have gone up to x, right? So it is 0.36 because it will be behaving as a simple beam. Okay, only the problems come with the slab part, that is the flange part. Okay, so the MC1 will be similar. It will be like beam. So it will be 0.36 into 20 into 250 into 200 into 412.5 minus 0.42 into 200, which is 118.3 kilonewton meter. Okay. In the slab part, what we will see is we will go with constant. Okay, 0.45 fck up to a depth of yf. Okay, so beyond that we don't consider that. Okay, so that is an extra cushion. Okay, extra factor of safety. Okay, so we'll not consider beyond yf. Okay, we only consider yf. Okay, we leave the part df minus yf. Okay, so mc2 is then becomes equal to 0.45 into fck into bf minus bw into yf into d minus yf by 2. So it is 0.45 into 20 into 600 minus 250 into 111 into 412.5 minus 111 by 2. So that comes out to be 124.8 kilonewton meter. Okay, so the total if you calculate how much it will be, if you take the total, it will be the moment carrying capacity of the T beam from the concrete, okay, due to concrete failure. So it will be 124.8 plus 118.3. So 124 plus 118 is 242, okay, 242, yeah, 242 will be the plus point 0.8 and point 0.3, it will be how much, 1.1, like 2 for it will be 243.1. So the moment capacity, carrying capacity due to concrete failure, it will be 240 3.1 kilonewton meter, okay. And if you see it from the tension side, okay, so it will be m equal to 0.87 into Fy into Ast into d minus df by 2, okay. So we have directly taken it from df, okay. So we've assumed that, so it is equal to 0.87 into 415 into 1964 into 412.5 minus 125 by 2, okay. So it comes to be 248.2 kilonewton meter, okay. So if we consider this, then we can say that concrete like concrete will fail first, okay, although it is quite near. But this is an approximate formula. Why? Because here we have considered this one, the lever arm as d minus df by 2, okay. But this is not correct, okay, because that is only the slab part, okay, the flange part, but web part it is d minus 0.42x, right? So therefore this is an approximate formula, not the actual. Actual is the this formula, okay. So from the concrete side, so from this we find that the actual moment carrying capacity from the concrete is 243.1, and the approximate formula from tension it is 248.2. So yeah, minimum if we take it is 243.1 kilonewton meter, okay. That is the moment carrying capacity of the T section given, okay. So with this we will come to the end of today's lecture, this week's lecture. So now let us go to the solve problems, okay. So the first problem is, consider the following statements concerning the limit state method of design of reinforced concrete. When the maximum strain in concrete at the outermost compression fiber is taken is 0.0035 in bending, that is true. And second is, the maximum strain in the tension reinforcement in the section at failure shall not be less than Fy by 1.15 Es plus 0.004, where Fy equal to yield strength of steel and Es equal to modulus of elasticity of steel, okay. So this is wrong. This should be 0.002, right? So yeah, so which of the above statements is or are incorrect, okay. A 1 only, B 2 only, C both 1 and 2, D neither 1 nor 2. So we just discussed, so this is correct. Outermost compression fiber have a strain of 0.0035 and bending, and the outermost tension fiber, okay, maximum strain it should be Fy by 1.15 Es plus 0.002, not 4, okay. So 2 is the incorrect option, okay, 2 only. So B is the correct option, okay. So as you can see, B is the correct option. So that is found from the partial safety factor for material gamma m, which is steel is 1.15, and using that in the maximum tension strain, tensile fiber strain. So that is Fy by 1.15 Es plus 0.002, okay. So yeah, so that is how to approach the first question. Second question is, consider the following statements regarding limit state method of design. Statement 1, for design purposes the compressive strength of concrete in the structure shall be assumed to be 0.67 by 1.5 times the characteristic strength. Statement 2, due to the size effect, the characteristic strength of concrete is reduced to 2 by 3 of its value. The partial safety factor is applied in addition to this, okay. So yeah, so what is the correct option? A, both statement 1 and statement 2 are false. B, statement 1 is true but statement 2 is false. C, both statement 1 and statement 2 are true and statement 2 is the correct explanation of statement 1. D, both statement 1 and statement 2 are true but statement 2 is not an explanation of statement 1. So yeah, so the correct option is C, okay. So both the statements are true and 2 is the correct explanation of 1, okay. So as I have I think I discussed with you last class also. So the uncertainty factor, okay, so we divide the FCK value two times, okay. One is by dividing one time we get 0.67, and by dividing the other time it is 1.5. This 1.5 is basically due to the partial factor of safety, this thing, okay. And this 1.5, okay, due to which we got 0.67, that is mainly because of the uncertainty, okay. So uncertainty is mainly coming from the size effect, okay. Size effect is basically when we try to find the compressive strength, we take 150 mm cubes, right? But if you see the normal structures, they are not 150 cubes, okay, they can be of any size, okay. So that, and they are always larger than 150 okay. So it can be a slab, it can be a beam, it can be a column, anything, right? So that's why it is not 150 cube, okay. So there comes the problem of size, okay, the size effect. So that's why to accommodate the effect, okay, we reduce the fck value initially to 2 by 3, which is 0.67, and then we apply the partial safety factor and divide by 1.5, okay. So that is the correct explanation of the first statement, okay. So C is the correct option. So as you can see, C is the correct option. So here also it is mentioned the characteristic strength of concrete is determined from the results of tests conducted on cube specimens of 150 dimension. The dimensions of concrete structures or in members of structure are different and widely varying. This has an effect on the strength of concrete in the structure. This is known as size effect. Due to this size effect, the characteristic strength of concrete is reduced to 2 by 3 of its value and then further divided by the partial safety factor of the concrete gamma m equal to 1.5 to get the design strength of concrete 0.67 FCK by 1.5 equal to 0.446 FCK. Okay. Yeah, so the third question, the depth of the neutral axis is calculated from the known area of steel, okay, and it should be A, less than 0.5 times the full depth of the beam, B, more than 0.5 times the effective depth of the beam, C, less than or equal to limiting value of the neutral axis depth, D, less than 0.43 times the effective depth of the beam, okay. So yeah, so the depth of neutral axis, XU, okay. So XU is calculated from the known area of steel, right? So if it is XU is this one, uh, if it is FE 500, XU will be 0.46. If it is 415, it is 0.48, and if it is D, okay, into D effective depth, and if it is FE 250, it is 0.53 D, okay. But this one, it should always be ideally less than or equal to limiting value of the neutral axis depth, okay. So in order to ensure that the best criteria is to have under reinforced section, and if even if it is not under reinforcement, at least it should be balanced, okay, not over reinforced, because failure in concrete is brittle, okay, but in steel it is progressive, okay. So ideally it should be either less or equal, okay, that is under reinforced or balanced. So C is the correct option. So as you can see, C is the correct option. So as you can see, for under reinforced section, the steel would yield first, but that does not result in whole section to fail because it is progressive. Okay, it will be indicative. So you would consider steel failure. But if you are considering concrete failure, the critical neutral axis would come into play, as that marks the limiting condition, as concrete failure is brittle in nature. Okay, so it is sudden failure. Okay. So summarizing, if under reinforced section, it will be actual neutral axis. If balanced section, it will be critical neutral axis or limiting value of the neutral axis depth. Okay, and even if over reinforced section, again it will be critical neutral axis or limiting value of the neutral axis depth, because concrete will fail at the balanced condition only. Okay, limiting condition only. Okay. So next question. So which of the statements is correct? Okay. A, axiomax by D is independent of grades of concrete and steel. B, axiomax by D is independent of grade of steel but changes with grade of steel. C, axiomax by D changes with the grade of concrete and steel. D, axiomax by D is independent of the grade of concrete and changes with the grade of steel. Okay. So axiomax by D, okay. So that is if you check it, okay. So that if from the similarity of triangles, if you see, it is mainly dependent on the strain values, okay. So strain of concrete is always constant, so it is 0.0035, okay. But the strain of steel, it is 0.87 fy by es plus 0.002, okay. So there the fy value of grade of the steel, that is the grade of steel, changes, okay. So based on this, the axiomax by D also changes. So this is 0.0035, but here Fy is variable. So it is independent of grade of concrete, but dependent with grade of steel. Okay. So D is the correct option. Okay. So as you can see, D is the correct option. So as I told you, axiomax by D equal to epsilon C by epsilon C plus epsilon S, which is equal to 0.0035 by 0.0035 plus Fy by 1.15 Es plus 0.002 is equal to 0.0035 by 0.0055 plus Fy by 1.15 Es. So Es is 2 into 10 to the power 5, but this is varying. Okay. So hence it changes with grade of steel. Okay. Next question. A doubly reinforced concrete beam has an effective depth d, effective cover of d prime to the center of compression reinforcement. What is the maximum strain in concrete at the level of compression reinforcement according to the limit state method? Okay, A 0.0035 into 1 minus d prime by d, B 0.0035 into 1 minus d prime by xu, C 0.0020 into 1 minus d prime by xu, or D 0.0020 into 1 minus d prime by d. Okay, A, B, C, D, which is the correct option? So according to limit state method, the maximum strain in concrete at level of compression reinforcement is B. Okay, 0.0035 into 1 minus d prime by xu, and that is that it comes out from the strain diagram. Okay, so from the similarity of triangles in the strain diagram. Okay, so the correct value is this 0.0035 into 1 minus d prime by xu. Okay, so that is the maximum strain in concrete at level of compression reinforcement as per LSM. Okay, so B is the correct option. Okay, and this, as I told you, strain in compression steel epsilon SC is 0.0035 into 1 minus d prime by xu. So you can refer here for finding it for more information. Okay, and also I have mentioned in the lecture also, in the slides also. So the sixth question: the dimension of a rectangular section is 250 mm by 350 mm. The clear cover is 25 mm. The tensile reinforcement is provided with three numbers of 16 mm Fe415 bars. The grade of concrete used is M25. Following are the statements regarding the above section designed by limit state method. A. The effective depth of the section is 317 mm. B. The section is an under reinforced section. C. The moment of resistance of the section due to steel is 86.67 kilonewton meter. Which of the above statements is or are correct? A 1 and 2, B 2 only, C 3 and 4, D 4 only. Okay. So effective depth, if we see, it is 350 minus 25 minus 16 by 2. Okay. So 25 minus 16 by 2 is 8, right? 25 minus 25 plus 8 is how much? 33, right? So it is 350 minus 33. Okay. So it is nothing but 370. Okay. So A is correct. Okay. So B, if you see, yeah, so AST is, if you see from the question, we get it to be 603.2 millimeter square, and depth of the neutral axis from equating the forces, we get XU by D is 0.305, and the limiting depth for FE415, right? Yeah, so it will be 0.48. So as 0.305 is less than 0.48, it is an under reinforced section. So 2 is also correct. Okay. And third question is moment of resistance due to steel, right? So it is 0.87 Fy AST into lever arm. So it comes to be 60 kilonewton meter. Okay, but here it is 86.67. So it is not correct. Okay, so statement 3 is incorrect. So which are correct? 1 and 2. So A is the correct option. So as you can see, A is the correct option. Seventh question: the dimension of a rectangular section is 250 mm by 350 mm. The clear cover is 25 mm. The tensile reinforcement is provided with three numbers 16 mm Fe415 bars. The grade of concrete used is M25. Following are the statements regarding the above section designed by limit state method. Okay. A. The percentage of steel provided is 0.76%. B. The position of neutral axis from compression side is 96.7 mm. C. The lever arm of the section is equal to 220.3 mm. D. The moment of resistance of the section due to concrete is 86.67 kilonewton meter. Which of the above statements is or are incorrect? A 1 only, B 3 only, C 3 and 4, D none. Okay. So if you see here, effective depth D is 350 minus 25 minus 16 by 2, which is 317 mm. AST is 603.2 mm square. Percent of steel provided is 0.76%. Depth of neutral axis is 0.305. This is similar to the last question. Okay, so here XU is 96.7 millimeter. So that is the position of neutral axis from compression side. So it is correct. Okay, so one is correct. Second statement is also correct. Okay, so percent of steel is 0.76%, and position of neutral axis is from compression side 96.7 mm. Okay, now the lever arm Z is D into 1 minus 0.42 x by D, right? So it is 317 into 1 minus 0.42 into 0.305, which is 276.3 mm, but here it is written 220.3 mm. So this is incorrect. Okay, and fourth question is, the fourth statement is moment of resistance due to concrete. So it is 0.13. Okay, so it is moment of resistance of the section due to concrete is 86.67 kilonewton meter, right? Yeah, so here it is moment of resistance, it is 0.138 FCK BD square. Okay, so 86.67 it comes out, but I think here one question, Yeah, one thing they should have written here, it is at balance section, okay, at limiting condition. I think they have forgot to write the question, write the this one the word. So it is at limiting, okay, limiting value. So limiting value, it will be 86.67 kilonewton meter, okay. So that way the fourth option is correct, okay. So that means the only option incorrect is the third, okay. So B. So B is the correct option, okay. But here we have to write one more word, that is the limiting, okay, balance, not the normal one, because then it will be 0.36 FCK BXU into D minus 0.42x. So it will be lesser, okay. So it is the limiting value. So then the eighth question, a T-beam is having the following dimension: width of flange BF equal to 1000 mm, depth of flange DF equal to 125 mm, width of web BW equal to 250 mm, overall depth of beam D equal to 250 mm, the concrete grade is M20 and the grade of reinforcing steel is Fe415, the clear cover is 25 mm. Consider a balance section having 25 mm bars. Which of the following is or are correct with respect to limit state method? 1. The neutral axis of the section lies within the flange. B. The T-beam can be designed as a rectangular beam. C. The beam area of steel required in balance condition is equal to 2058 millimeter square. 4. The moment capacity of the section is 127.5 kilonewton meter. Okay. So which is correct? A 3 only, B 1 and 2, C none, D all. Okay. So let us see. So D is 250 minus 25 minus 10 is 215 mm. XU is 0.48 D. Okay, because it is already written balance. Here it is written balance. Okay, so it will be limiting, and it is 415. So it is 0.48 D, which is 103.2 mm. Okay, which is less than DF. That means this one, it is case 1. Okay, it is case 1. So hence the neutral axis lies within the flange and the section can be treated as a rectangular beam. Okay. So both are correct. Neutral axis of the section lies within the flange. Okay. And the T beam can be designed as a rectangular beam. Okay. So both are correct. Then area of tensile reinforcement AST is equal to XU by D into FCK by FY into 0.36 by 0.87 into BFD. Okay, so B will come converted into BF, right? And this is equating the forces in tension and compression. So we get the value as 2015 millimeter square. So that is area of tensile reinforcement. Okay, so this is correct. And third is moment carrying capacity of the section. So it is 0.36 FCK BXU into D minus 0.42x. Okay, so here instead of this you can also use 0.138 FCK BD square. Okay, so yeah, so even if you use the 0.13 FCK BD square, so yeah, so even if you use 0.13 FCK BD square, it comes to be 127.5 kilonewton meter because it is limiting. Okay, but the previous question that was not. Okay, so we have to correct that. And because it is a balance section, moment carrying capacity of concrete and steel will be same. Okay, both side if you calculate, it will be the constant. Okay, so ninth question. The rectangular beam of width 250 mm is having effective depth of 327 mm. The concrete grade is M20 and the grade of reinforcing steel is Fe415. Considering the section to be a balance section, calculate the area of tension reinforcement needed with regard to the limit state method. Okay, so answer option is A 602.3 millimeter square, B 782.52 millimeter square, C 948.23 millimeter square, D 1256.64 millimeter square. Okay, so which is the correct option? Okay, so if you see effective depth D is 327 mm, depth of neutral axis. So because it is a balance section, yeah, balance section. So it will be XU max by D. Okay, so it is 0.87 FYASD by 0.36 FCK BD. Okay, this is the equation, and XU max by D will be 0.48 because it is balance for Fe415, right? Yeah. So using these two, okay, so we can find the AST value as 782.52 millimeter square. So B option is the correct option. So as you can see, B is the correct option. And last question, the rectangular beam of width 300 mm is having overall depth of 400 mm. The concrete grade is M20 and the grade of reinforcing steel is Fe415. The tensile reinforcement is provided by 420 mm bars. In the compression side, the reinforcement is provided by two 60 mm bars. The clear cover is 25 mm. The saline points of design stress strain curve of Fe415 is given by this one 0.00144288, 0.00163,306, 0.00192,324, 0.00241,342, 0.00276,351, 0.00380,360. Consider the following statements. 1. As per limit state method, the section will take additional moment of 25 kilonewton meter. 2. The stress in steel at compression level is equal to 359.3 megapascal. 3. The section is over reinforced. 4. The moment of resistance of the whole section is 110 kilonewton meter. Which of the above statements is or correct? A 3 only, B 1 only, C 1 2 and 4, D 1 3 and 4. Okay. So here effective depth comes to be 365 mm. Effective covering compression side is 333 mm. Okay. Tensile reinforcement 1256.63 mm square. Compression reinforcement AC 402.12 mm square. XU it comes to be uh, yeah. So yeah, XU, that is the limiting value. So it comes to be 0.48. Okay, 0.48 D, which is 175.2. Okay, so moment of resistance. Okay, so because it is a this one, right? Yeah, so okay, so moment of resistance corresponding to a balance section, because it is a doubly reinforced section, right? So we are taking XU. Okay, so moment of resistance corresponding to a balance section, MU, the limiting values. Okay, so we are taking limiting values because of doubly reinforced. So MU1 equal to 0.138 FCK BT square, which is 110.31 kilonewton meter. Okay, and using the equation, equating the forces, we get AST1 as 1048.14 millimeter square. Okay, so corresponding to the balance section, that is singly reinforcement, AST1 is 1048.14 mm square. Okay, and the extra additional tensile reinforcement available is 1256.63 minus 1048.14, which is 208.49 mm square. Okay, so the additional moment of resistance due to the additional tensile reinforcement, MUST2. Okay, it is 0.87 into FYAST2 into D minus D prime, which is 25 kilonewton meter. Okay, so that means the first statement is correct. Okay, so statement 1 is correct. Therefore, moment of resistance due to steel is 110.31 plus 25. Okay, that means 135.31 kilonewton meter. And strain in compression steel epsilon SC is 0.0035 into 1 minus d prime by xu, right? Which is equal to 0.00284. So using the given points, okay, mentioned in the question, okay, saline points. So at 0.00284, okay, the FSC value comes to be 351.69 Newton per mm square through interpolation. So here it is written 359.3 megapascal. So it is incorrect. Okay, and therefore mu2 is FSC ASC into d minus d prime, which comes to be 46.95 kilonewton meter. Okay, so moment of resistance due to compression steel and concrete, that is at a due to concrete failure, it is 110.31 plus 46.95. So that comes out to be 157.26 kilonewton meter. Okay, so because in steel, okay, steel it was how much? Steel it was 130, steel failure it was 135.31, and concrete failure it is 157.26. That means it is a, it will fail in tension. Okay, so it is under reinforced. Okay, so it is governed by yielding of steel first, so under reinforced. Okay, so that means this is over. So statement 3 is incorrect. Okay, and total moment carrying capacity of the whole section will be minimum of 135.31 and 157.26, that is 135.31 kilonewton meter. So it is not 110 kilonewton meter. Okay, so that means statement 4 is also incorrect. So only one is correct, 2 3 4 are incorrect, so that is one only. Okay, so B option is correct. B option is correct, as you can see. So yeah, so with this we come to the end of today's lecture. Before ending, I would like to suggest everyone, advise everyone to please practice the problems. Okay, so more you practice, more you will understand. Okay, so because lack of time, I am not able to manually do it, because otherwise the course will not get completed. But please take your time and please practice as much as possible the problems we discussed. Okay, so it will help you in the later part. Okay, so later on for exams as well as for future, you will have grip over the subject. Okay, and that because it is a basic subject. Okay, in RCC is the basic subject for civil as well as in structural engineering. So please take your time and understand the concepts. Okay, so yeah, so with this I would like to end today's class. Okay, so let us meet next Sunday and have a great week coming. Okay, so with this I would like to end today's class. Thank you. Yes. Hello.